years of experience as far as hydrogen, huge hydrogen production facilities in Norway is concerned. And as you all know, Norway is one of the first countries which started with establishing a setup for hydrogen strategy. And as you all know, the world's first hydrogen ferry that is in Norway. So Norway has ambition to become carbon free by 2050, and before 2030, Norway has ambitions to reduce the carbon output by 60% compared to 1990. So hydrogen is going to play a big role. So Norway has focused on hydrogen. So we have established two different environment-friendly energy research centers on hydrogen and ammonia in Norway. One is called High Value, and the other one is, of course, Hydrogeny. We HUL are part of High Value, so my colleague will explain what we are working on in these energy centers later on. So as far as these courses are concerned, we have been offering 3 courses in Norway. One is hydrogen for decision makers, and the other one is hydrogen for management and administration, and the third one is hydrogen for technical personnel. So today we are going to offer this course for Sri Lanka and India, and we would see how we go further from here. The objectives and the details of these courses, of course, will be given by my colleague, Dr. Jonathan, later on. So now I will call upon my colleague, Dr. Velaug Mirset Ortadal. She is an associate professor at HUL. At the same time, she is the associate director or deputy director at this high value energy center in Norway. So you could share, Velaug, you are there?
Yes, I am here.
Okay, I will just stop sharing so you could start. Velaug. Welcome, Velaug.
Thank you, Dayalan, for the introduction. And it's very nice to be here today and meet some of our friends from India and Sri Lanka again. Thank you for the invitation. We met some of you in India in September this year, and that was very nice. Like Dayalan said, I will just, let me just share my screen first. I will first give a very brief introduction to our research center, High Value. I am the center deputy of the center, and then I also work as an associate professor at our university, Western Norway University of Applied Sciences. So the Norwegian government launched a hydrogen strategy a couple of years back. And this strategy included awarding hydrogen hubs and some pilot projects within a few years, and within 2030, realization of full-scale hydrogen projects in the industry. And this hydrogen strategy also included research. So the establishment of dedicated research centers on hydrogen and ammonia. So last year, our research center, High Value, was awarded, and we started our work. This is a research center that is going to last for 8 years, and we are financed then partly by the Norwegian Research Council, and partly by own financing from each of our partners. Now, let me just organize my screen a bit. The work that we are going to do, we have divided into 6 different topics or work packages that together will cover the whole value chain of hydrogen. So when establishing hydrogen technology, it's not just technical aspects that are important, but they are also important. So we cover everything from novel production methods, through storage technologies, distribution and transport of hydrogen, and all the way to end user applications. So these are the technical areas, but it's also important to, if we want to succeed, it's important that we also look at the whole picture. So we have also included safety and risk science aspects. How can we build this hydrogen economy in a safe way? We have also included social, societal aspects. Will people accept this new technology, and how can we embed it in society in the best way? And finally, we have included rules, regulations, business models, markets. How can one do this in a way that is profitable? And if we take all of these aspects into account, we believe that we can build a robust hydrogen economy. So there are two important aspects. First, you need to look at the whole value chain, not just individual parts. And secondly, we need to collaborate to succeed. We need to collaborate across different sectors, and we need to work interdisciplinary to succeed. So to manage this, we have joined forces with these partners. We have about 50 partners in our research center. We have 7 national research partners and 4 international research partners. And then we have about 45 other user partners that span all the way from the private sectors, from energy companies to law firms. We have industry clusters, we have technology providers, we have suppliers, we have partners from the public sector, so like municipalities are our partners. And we also have Norwegian representatives from Norwegian authorities. So we have the Norwegian Maritime Authority, for instance, as one of our partners. So we believe that together we can solve at least some of the challenges that we will be facing if we want to transition into a zero-emission society based on hydrogen technology. So we believe that together we can solve the challenges that lies ahead of us in the whole value chain. So from production to storage, different storage solutions, distribution and transport, and all the way to end users, covering both the maritime sector and in industry on land. So through research, education, and collaboration, we believe that we can facilitate a safe and sustainable development of value chains for hydrogen and hydrogen-based fuels in industry and society. So thank you. That was a very brief introduction to our research center, and you see the contact information there if you have any further questions. Then we will continue into the learning sessions. And I will introduce, I hereby give the word to my associate professor at our university. He has a PhD in chemical engineering. He's doing research here, and he's also teaching hydrogen courses for industry, so lifelong learning courses in hydrogen technology. Dr. Julia, she has a PhD in material science with a focus on materials for energy applications. She is also an associate professor, and she's also teaching hydrogen courses for industry at HVL. So both of these play a central role in the hydrogen team at our university, and they will now give us a crash course in hydrogen technology. Please, Jonathan, the word is yours.
Thank you very much, Vela, for that kind introduction. As I ask my students, can you see my screen now?
Yes.
Thank you. So today, me and Julia will take you through this hydrogen for decision makers, which is like a taste of hydrogen and what it can become. And we will be the main speakers, but I want to emphasize the importance of our team. So Dailan, he is the engine behind this, a real power behind this effort. And then, as Vela just said, she is the leader of co-deputy of this high-value hydrogen research center. They will speak during these sessions, but me and Julia will be the main presenters. I will soon give the word to you, Julia, but here you can see the agenda, which she will present. But before that, I want to just emphasize that it will be 2 times 45 minutes. So we will have 45 minutes, then a break, and then we'll continue. Then, Julia, the floor is yours.
Thank you for the introduction. I will also share my screen. So, just a second. Yes, thank you very much for the introduction and for the possibility to be a part of this webinar. As Jonathan already mentioned, we want to give overview of hydrogen technology or hydrogen in nutshell. So I will start with a brief introduction of why are we interested in hydrogen and what hydrogen is, which property it has, and then I will start with introducing different production methods for hydrogen. I will talk about production methods from of fossil fuels, and then Jonathan will continue with electrochemical hydrogen production, and then he will talk about storage and distribution of hydrogen, about use of hydrogen, and then we will close up with final remarks. So why are we so interested in hydrogen? Thomas Edison, in the beginning of the last century, told the following: you see, we should utilize natural forces and thus get all our power. Sunshine is a form of energy, and the wind and tides are manifestations thereof. Do we use them or no? We burn up wood and coal. As renters, we burn up the front porch for fuel. We live like squatters, not as if we owned the property. So now let's see if anything has changed since the Edison times. The global energy consumption has increased drastically in the last century, and it will continue to grow. And if we look at the distribution of energy consumption by energy type, it is clear that the world is still heavily dependent on fossil energy. Oil and coal are the dominant energy sources, with gas in the third place. But we could no longer burn our own front porch for fuel, as Edison said, and therefore countries all over the world set efforts to reduce their greenhouse gas emissions. Thus, Norway and the European Union set the goal to reduce CO2 emissions by 55% by 2030 and to establish a sustainable transition to net zero greenhouse gas emissions in 2050. India announced in 2021 that it aims to reach net zero emissions by 2070 and to meet 50% of its electricity requirements from renewable energy sources by 2030. And the Sri Lankan government set a goal of achieving 70% of renewable energy generation by 2030, and it aims to become carbon neutral by 2050. The use of renewable energy sources is essential to ensure a sustainable future, um, but renewable energy is intermittent, and green hydrogen could be the solution to the intermittency issue of renewable energy. Hydrogen and hydrogen carriers would also allow to transport energy from regions with abundant solar and wind resources to energy-hungry regions, as for example from Norway to Europe or from Australia to Japan. And it's also been discussed that India can export green hydrogen to Europe. Um, um, Hydrogen will also contribute to decarbonization of transport, especially for heavy duty or long distance transport, and for the decarbonization of industry, both as energy carrier and as feedstock. But what is actually hydrogen? So hydrogen is the element number 1 in the periodic table of elements. It is the lightest element. A hydrogen atom consists of negatively charged electron, which is orbiting positively charged proton. Um, um, Hydrogen is the most abundant chemical substance in the universe, and in mass percentage, hydrogen makes up 74% of all atoms in the universe, and over 90% by number of atoms. So stars, such as the sun, are mainly composed of hydrogen in the plasma state. Hydrogen plasma consists of hydrogen ions, separate protons and electrons. And the sun's energy production is the result of the nuclear fusion of hydrogen to helium. So every second, 4 million tons of hydrogen are fused on the sun and are converted into helium and energy. So hydrogen warms up our Earth. On Earth, most of hydrogen is chemically bound as water and hydrocarbons. And even in our body, the third most common element by weight is hydrogen. But hydrogen, about which we will talk today, is molecular hydrogen or dihydrogen, because it consists of 2 hydrogen atoms. So 2 hydrogen atoms come together and share their 2 electrons in a covalent bond. So molecular hydrogen or H2 molecule consists of 2 hydrogen atoms sharing their electrons. So a little bit about properties of hydrogen. It is a colorless, odorless, and non-toxic gas under normal conditions on Earth. It has minimal health hazards as gas. However, it can lead to suffocation by substitution of oxygen, or if we have a liquid hydrogen, it possesses a coal burn hazard. Hydrogen is 40 times lighter than air, and it also influences how. So, for example, if there is a hydrogen leak, hydrogen will very quickly mix with air, and the mixture is extremely explosive. But at the same time, if the leakage happened outside, hydrogen will disappear very soon, and the hazard will be lowered. So hydrogen molecules are very small, and therefore it is very difficult to design equipment which is hydrogen tight. It leaks easily, and as it is colorless, odorless, and not toxic gas, it is difficult to detect hydrogen leaks without special sensors. Also, small hydrogen molecules easily penetrate into the crystal structure, for example, of different materials, for example, into metals, and it leads to mechanical failure of the materials, so-called hydrogen brittleness. As I already mentioned, hydrogen is extremely flammable. It has extreme fire hazard. It is combustible in a wide gas-to-air volume ratio. If we look at this diagram, which shows a gas-to-air volume ratio where which is flammable. Hydrogen is flammable between 4 to 75 volumetric percent. And for example, natural gas just from 5 to 15. Also, hydrogen requires a minimum energy for self-ignition if compared to other gases, to natural gas or propane. So leaks also have a tendency to self-ignition. If we look at the table with properties of hydrogen compared to properties of methane, we can see that the boiling point of hydrogen is almost 100 degrees C lower than for methane. So hydrogen has the second lowest boiling point and melting point of all substances, only after helium. It means that it is extremely energy we need to put a lot of energy to liquefy it. Also gravimetric energy density, that means energy per kilogram of hydrogen, is at least 2 times higher than for methane. It has very low volumetric energy density, so it is energy per liter of hydrogen. And it is due to its low gas and liquid densities. So as a result, we get a low volumetric energy density. So energy density of hydrogen is almost 3 times lower than of a liquid natural gas. And as I already mentioned, compression and liquefaction are energy-intensive processes, as we need to cool down hydrogen to up to 253 degrees C to liquefy it. Also hydrogen possesses challenges in storage and transport. Most of the hydrogen is bound as water and hydrocarbons on the Earth, as I have already mentioned. Therefore, the hydrogen production is about going from hydrogen carriers to hydrogen, and this requires energy. Let's have a look at the global hydrogen production by source. second. So over 50 so the most of hydrogen is produced based on fossil fuels, and just 4% comes from the renewable energy sources. And so fossil fuels are the main sources of hydrogen production. At the same time, 6% of global natural gas consumption is used for hydrogen production. And more than 50% of hydrogen which is produced is used to produce ammonia. The availability of green hydrogen, as you can see, is very limited, and the reasons for this are that we need to increase renewable energy production, and we need to reduce the cost of electrolyzer technology to reduce the cost of green hydrogen. Hydrogen comes in different colors in dependence on its production methods. So this rainbow classification of hydrogen production methods is not very strict for some of the colors, but black, brown, green, and blue colors are used consistently. So gray, black and brown hydrogen is from gasification of coal. Gray is for steam methane reforming, and it is the most widely used process for generation of hydrogen. So blue, it is also steam reforming of natural gas, but with CO2 capture. Turquoise hydrogen comes from pyrolysis of natural gas. Yellow comes from electrolysis from electric energy from grid, so mixed energy, both from renewable sources and fossil. And then pink hydrogen is produced with water electrolysis using electricity from a nuclear power plant. Besides pink, there are also two other colors associated with nuclear energy. It is red hydrogen. Red hydrogen is generated through the high temperature catalytic splitting of water using nuclear thermal power as the energy source, and purple hydrogen is obtained by using nuclear power and heat through combined electrolysis and thermochemical water splitting. So green hydrogen, which is also often called clean hydrogen or renewable hydrogen, or also low carbon hydrogen, is by definition the hydrogen produced with water electrolysis using electricity from renewable sources. And finally, white hydrogen corresponds to the exploitation of subsurface sourced natural hydrogen. Now we will have a more closed look at this hydrogen production methods. But first, so first I will start with naturally occurring hydrogen. So our countries have committed to cut the greenhouse gas emissions, and to make it happen, we should start with ourselves, and we should reduce our carbon footprint in all the spheres of life, as for example in cooking. Charcoal and non-sustainable wood with high carbon footprint is used for example, barbecuing and tenders. But why not to prepare food on hydrogen instead? And I know at least one nice place for barbecuing with hydrogen. In Turkey, there is a mountain which is called Chimera. The mountain is named after a fire-breathing creation from ancient Greek myth. So on this mountain, a hydrogen-rich natural gas seeps to the surface and gets ignited spontaneously in the sun. So these chimera flames are the results of metamorphic activity releasing the gas. And these flames has been burning for thousands of years, and they are believed to be the source of the first Olympic flame in the Olympic Games in ancient Anatolia. And now it is a popular, Chimera Mountain is a popular touristic location where tourists come, for instance, to barbecue their food on hydrogen. But many of them even don't realize that it is hydrogen what they use for grilling. So here are just two examples that for example, barbecuing is very popular in Australia, and that's why University of Sydney developed the world's first hydrogen barbecue, which is now commercially available. And Tokyo Olympic flame was also inspired by this lighting torch by hydrogen in ancient Anatolia. So Tokyo Olympic flame in 2020 was the first powered by hydrogen. There has been a prejudice that free hydrogen in nature is rare, and the reason for it is that in gas chromatography, hydrogen is often used as carrier gas, and gas chromatography used to analyze gases when nature, like so there are only a few modern portable gas analyzers which include hydrogen sensors and their design. And therefore, it is difficult to estimate how many times hydrogen hasn't been identified in hydrogen-rich samples due to the lack of suitable detection techniques to measure hydrogen concentrations. Also, there are several processes involved in natural hydrogen formation, and some of them are also not well understood yet. For example, hydrogen naturally occurring hydrogen can originate from the Earth's mantle of core. So in the Earth's deep mantle, hydrogen is stored in minerals, and at the conditions in the Earth's mantle, there is high pressure and high temperature, and hydrogen is released from this hydrous minerals. So another process for how hydrogen can be natural hydrogen can be formed is called serpentinization. It is a metamorphic process where rocks come in contact with water and get oxidized to a mineral which is called serpentine, and hydrogen is released also alongside with methane. Here is the reaction, how it actually happens. Another possibility how natural hydrogen is formed is natural water radiolysis. So there are natural minerals which contain uranium or plutonium, and when they come in contact with water dissociate and hydrogen is released. Also, hydrogen can be produced by biological activity, by fermentation, for example, or by nitrogen-fixing bacteria. So naturally formed hydrogen appears as a promising carbon-free and abundant source, but there is a low level of research on this topic. Therefore, it is difficult to say how large, how many, how much white hydrogen do we have worldwide, and it is also difficult to estimate which infrastructure is required to exploit it, and also how sustainable this process of mining white hydrogen will be. In different countries, there are a number of initiative where scientific community and industry come together to exploit this possibility of mining natural hydrogen. One example is a European initiative for subsurface hydrogen. And for example, recently in France, was discovered in the Lorraine area, there was discovered a large hydrogen deposits, which are believed to be the largest in Europe, but it is still unclear how to extract it. And here we can see discoveries of hydrogen, where hydrogen concentration is larger than 10 volumetric percents all over the world. And this is data from 2020. Now there are probably more points on the map because the activities of looking for natural hydrogen are increasing. So yeah. Now we come to the next color, the next two colors of hydrogen, which we briefly mentioned. That is gray and blue hydrogen, and both come from steam reforming of natural gas. Gray is steam reforming of natural gas without carbon capture, and blue hydrogen is with carbon capture. Steam methane reforming is a process in which methane from natural gas is heated with steam, usually using catalysts such as nickel. And a mixture of carbon monoxide and hydrogen is produced. And then there is another step in this process. It's called water gas shift reaction, where carbon monoxide reacts again with water to produce more carbon dioxide, more hydrogen and carbon dioxide. Yeah, and I wanted to mention that 80% of all hydrogen produced today is so-called gray hydrogen. And now we will have an overview of this production methods, which I briefly mentioned. So why hydrogen is naturally occurring, and we don't know how much white hydrogen there is in the world and how we can extract it. And then from fossil fuels comes gray and blue hydrogen, both from steam methane reforming, one gray without CO2 capture and blue with CO2 capture. So steam methane reforming is a two-step process consisting of reforming and water gas shift reaction. And another a method to obtain hydrogen from methane is partial oxidation. It also catalyst is needed here, and here methane is incompletely combusted with oxygen. And the next method is autothermal reforming, which combines steam methane reforming and partial oxidation in one process. So steam methane reforming is and the thermal process. It requires heat, and partial oxidation is exothermal process. It gives up heat, and when we combine these two processes, the heat from partial oxidation can be used for steam methane reforming, and the process is more efficient. The last two methods of hydrogen production from fossil fuels are gasification of coal and pyrolysis of natural gas. And gasification of coal is the oldest method of hydrogen production, and 80% of hydrogen nowadays is produced with this method. And the last method is Turkey's hydrogen. It is pyrolysis of natural gas. In the pyrolysis process, methane is directly separated in hydrogen and solid carbon. And solid carbon is much easier to handle than the gaseous carbon dioxide produced in steam methane reforming, and it is also available process for industry, available product for industry. And so now I would love to give the word to Jonathan, as he will continue with hydrogen production from electrolysis. Please.
Thank you very much, Julia, for that nice presentation. I will now continue with electrolysis. So let's see now. I hope that you can see my screen. So electrolysis, it's about 4% of the world's hydrogen production, but we give it so much attention because we hope that in the future it will be the dominating or one of the dominating production methods. So to your right there, you can see different types. So the first one, this is a lab module, and I brought it here. I actually opened it up. Here you can see inside. It looks like this. And if you look at the figure, it has a very complicated structure on the inside. Now, we will not spend so much time on this structure, but we can just imagine that water is coming in, and that there is a catalyst here. And what you get out is oxygen and hydrogen. I also brought a module which is slightly bigger. So you might imagine that this will produce a lot of hydrogen, but it's actually just 0.0 grams of hydrogen per minute. At a glance, we have a very complicated chemical way of producing hydrogen. But of most important is that all electrolyzers, they are the same. You have something that will conduct ions, and you have a reaction that in the end, no matter how you do it, will take in water here and produce oxygen gas and hydrogen gas. In this system, we actually have many types of ways of doing it. So what I just showed you was a picture of a PEM electrolyzer, but there is a world out there of electrolyzers. The most common ones are alkaline and PEM, which are low temperature, and solid oxide electrolysis, which is high temperature. Now, I think that this gives a proper overview, and this is the most important to know. What we are interested in is not the chemical reactions, but we are interested in the operating temperatures. So if we look at the low temperature electrolyzers, they typically are good because they require not that much heat to operate. This is good in terms of its combination with, for instance, a variable power source, because in order to use this, you need to put on some power. Now, as Dylan said, 100 years ago in Norway, we used alkaline electrolysis. It has gained a lot of attention because it uses a catalyst that it's very common. This nickel is a very common metal. It has a relatively high efficiency, and it's one of the most common techniques in terms of electrolysis to produce hydrogen. I think you have some of you have heard about PEM electrolysis, which is maybe the cousin of the more modern variant of low temperature electrolysis, and it's the same principle, but here you see that the catalysts you use are noble metals. And this is a problem, right? Because if you use noble metals, you need to typically mine them from somewhere, which is a disadvantage, both in terms of the fact that they're not as abundant, and also that the mining business has some very bad consequences for the environment. So in the low temperature, it's a competition between PEM and alkaline. So I think that these two techniques, they will coexist side by side. It's worth noting, as you might have understood already, that this alkaline technology, since it's been used for almost 100 years, it's a mature technology. While this PEM also mature, not as mature as the alkaline, which has been around since the 60s. Common for these two low temperature technologies is the fact that they are in use today commercially. However, a competitor is this high temperature electrolysis, which operates between maybe from 500 to 1100 degrees. Who knows how this will be in the future, but it's worth noting that if you have such a high operating temperature, you will have problems with your material. So choosing and designing material to get this work is quite challenging. It's also worth noting that when you use this high temperature, it gives you some advantages in terms of what gases you can produce. You can not only use this for hydrogen production, and also, if you think about the fact that these also exist as fuel cells, you have a multi-fuel system. High temperature means that you can use a lot of different chemicals in this system. Now, as you see here, the biggest problem so far is that this type of electrolysis is in the R&D phase. And there's a lot of effort going on into making this into a mature technology. The main reason is that we see that it has some advantages if we solve the fact that we need such a high temperature. So we are trying to, or researchers are trying to get temperature of this down as far as they can. Electrolysis is very nice to use with, for instance, a variable power source. And one of the variable power sources we have is offshore wind. And then I would like to give the word to you, Veiler, to tell us a bit about offshore wind. And yeah, thank you.
Thank you, Jonathan. So, like Jonathan and Julia said, most of the hydrogen today is produced from natural gases, from fossil fuels, and this releases a lot of CO2. So if we in the future want to make this into a green industry, we need to produce hydrogen using electricity and using clean electricity. So this means that if we're going to have electricity for producing hydrogen, and also then electrify different sectors, we will be needing a lot of new additional clean energy. And one of the new energy sources that are emerging now is offshore wind. So in different parts of the world, this is an emerging market. And the image that you look at here is from a project that we did together with Greenstat a couple of years ago, where we looked at the possibilities of having production of hydrogen on an offshore platform directly from the wind power. So the question is, when we build these offshore wind farms, is it better to take the electricity back to shore and then use it on shore? Or can we actually advantageously use the electricity on site, close to where it is produced, and have a hydrogen production facility offshore, produce hydrogen-based fuels, and then, as you can see on this image, is also pictured a fueling station that bunkers directly to a ship. And the study we performed concluded that this is actually a feasible option, and it can actually lower the price of the produced energy. Next slide, Jonathan. So we are looking into different research aspects of how to produce hydrogen, either from an offshore wind farm or from what we call trapped power. So trapped power is, in Norway, we have this situation along the coast of Norway, that many of our hydropower plants have the possibility to produce a lot of hydrogen, but our grid is not strong enough, so we can produce more power than we can actually transport away from the hydro plants. So this means that a lot of the hydro plants are not producing as much as they can, or they're not producing at all because the grid is not ready. And then one possibility then is to install an electrolyzer on site close to the hydropower plant and produce directly from there. And then we are also looking into different aspects of hydrogen production from offshore wind, and also how to store it. So hydrogen is a bit difficult to handle because it takes a lot of space to store hydrogen gas. Or like Julia said, if you want to have it as a liquid, you need to cool it down to extremely low temperatures, minus 253 degrees Celsius. So it's difficult to contain pure hydrogen, but there are some alternatives that I think my colleagues will talk about later. You can transform it into, for instance, ammonia, that is easier to handle, and then we are looking into different options. What is the best way to store the hydrogen offshore? And then you also need, if you produce it offshore, you need to either use it on site in a fueling station directly to ships, or you need to transport it to where you want to use it. So either by pipelines or perhaps by ships to shore. So these are research topics that we are working on within our Hydrogen Research Center, and we have a PhD student working on this. So then I think I will give the word to Dialan, that will say a few words about what his research group is doing on different production methods. Please, Dialan.
Thank you, Ella. Thank you, Ella. Thank you, Jonathan. As both Julia, Jonathan, and Bela pointed out, actually now the majority of the market as far as market is concerned, is a gray hydrogen which dominates the market. But of course it is very cheap as well compared to other hydrogen production technologies. So we are focusing on two things. One is electrolysis, the other one photoelectrolysis. The thing is, as everybody pointed out here, the primary concern now is if hydrogen could be competitive to other technologies, the prices of production of hydrogen must come, drastically down. That is important. Now the green hydrogen, which is produced by electrolysis, it costs nearly 4 times compared to the gray hydrogen. So that is the challenge we all face. So we had to work on different type of technologies, such that we could reduce the prices. That is the primary thing. So we are working on electrolysis. We are working on, as Jonathan pointed out, the PEM and alkaline based hydrogen technologies. But there, of course, you are, as Jonathan said, we are using iridium, platinum, palladium, these type of expensive material. So we have to work on materials which could be cheaper. That is one thing we have to work on the electrodes. That is one thing. The second thing, of course, as well I pointed out, there are many places you produce energy with maybe hydro, maybe solar, maybe wind, but your grid is not stable. The grid is not good enough to cope up with this type of extra energy. That is a problem. Even in Sri Lanka and India, I know the grid is the challenge. So even though you produce a lot of energy from solar farms, you cannot use it. So in that sense, we have to find out methods to use the solar energy to produce hydrogen. One way, of course, everybody knows, that is PV electrolysis. The other methods are photoelectrochemical and photocatalysis. Um, Jonathan, next slide, please. So we are focusing, as I said, on two things. One, of course, electrolysis. We are working on alkaline and PEM electrolysis, but we are working on the electrode materials. We want to make cheap materials, which could replace platinum, gold, Ag, and iridium, and so forth. So we have collaborations both in India and Sri Lanka working on these materials, new materials. That is one thing. The second thing, of course, we are trying to work on solar energy directly to produce hydrogen. We call it photocatalytic hydrogen production or photoelectrochemical green hydrogen production. So what we do is we are working on nanomaterials which could absorb the sunlight, and it could, in reaction with the water, it could produce hydrogen and oxygen. The technique is very simple, such as photosynthesis. What happens is you have a nanomaterial which absorbs the sunlight. It's a semiconductor material. What happens is the electrons from the valence band, it comes to the conduction band, and it leaves the holes behind. Then the electrons go into the water, and you get produce hydrogen, and of course holes with the water, and you produce oxygen. This is the simple technique we use, but this is a known technique, but people have been working for the past 50 years. But now people have been working on new materials. All these development in nanotechnology has resulted in we could work on these materials at the lab level. So we are working in the labs, and we see that these materials could produce hydrogen, not a problem, but we have to separate hydrogen and oxygen. That is the concern we are working on. The other thing, of course, they can use these materials as electrodes. That is called the photoelectrochemical method. Then, of course, you could separate hydrogen and oxygen with membranes. So these are the techniques. I think it is still in the lab level. We have this high value center. There we have these projects here in Norway. I think in the future, there may be, I think in 5 to 10 years, there may be activities you'll be hearing about photocatalytic hydrogen production in a grand scale. In Asia, in South Asia, Japan, South Korea, there are companies which are working on these things. So, but here we are still in the lab level. Even in Southeast Asia, is in the lab level. So these are the methods which will be dominating in the future to produce cheap, flexible hydrogen production. Thank you, Jonathan. You could just proceed.
Thank you, Dylan. I think that now, if it's okay, we'll have a 15-minute break. And we'll be back here at 9:30.
9:30 Norwegian time, so it's around 15 minutes.
Yes,
15 minutes from now. 15 minutes from now. It's, I think, 2 o'clock in Sri Lanka and India.
I think so too.
Yeah, at 2 o'clock. We'll meet again at 2 o'clock Indian Sri Lankan time. Thank you, Jonathan. Yes.
Let's now imagine that we have produced our hydrogen. We could use natural gas for steam reforming, or for instance, natural gas to decompose it into hydrogen. Or we can use electrical power, as Velo said, from offshore wind or from a waterfall and do electrolysis with, for instance, this thing, and then make hydrogen. But the question now is how to store it. And obviously, storage is a complicated field with a lot of possibilities. We have many ways, but we typically divide them into two different categories: physical or chemical storage. Obviously, we can have it as compressed hydrogen. And now you understand why we need to compress it, because as Julia said, hydrogen has a really, really, really low density. So if we do nothing, we will have actually no hydrogen molecules in our volume. We can liquefy it. We'll see shortly that this is a really complicated process, which really is difficult, but it gives us even higher hydrogen density. Or we can absorb it onto, for instance, a particle or inside a metal. So if we do physical storage, these are the typical for compressed and liquid hydrogen. Now, they have some disadvantages, and that's the fact that if you have a container with compressed hydrogen, you can have a leak. So another possibility is to do a chemical storage. Now, a chemical storage can be like this. We can use metals and put hydrogen inside the metal. Or we can use a class of organic molecules called liquid organic hydrogen carriers. And the illustration is here to your right. You have some molecule, and by using a catalytic reaction, you can either load it or unload it with hydrogen. So it's like a reversible hydrogen storage medium, like a battery, and you can compare it to maybe like an olive oil, where you put hydrogen in or you take hydrogen out of. Lastly, you can convert the hydrogen to, for instance, ammonia or methanol. So the good thing with, for instance, ammonia is that we have used it for a long time. So it's more mature and in that sense, safer for us. Okay. Remember that when we use hydrogen, we need to be careful about its purity. We will see later that we can use it in a fuel cell, and then we need a high hydrogen purity to not destroy the fuel cell. But we also need a high purity when we store it. So in our system, we have a lot of components then that can be destroyed or disturbed by impurities. For compressed gas, we need a relatively high purity, but for liquid, even higher. And the reason for that is this liquefaction temperature. So we need to get down to minus 250 degrees Celsius, which is 20 degrees above the absolute zero. So at this point, everything freezes. So we need to be really mindful of the fact that we have a highly pure hydrogen. How do we do this? For hydrogen storage and transport, we can obviously use compressed or liquid. In the case of compressed, we are lucky. We can use regular compression methods, which we can use for any type of gas. But we also have some really advanced compression methods that are kind of new for you, maybe, in terms of hydrogen. So the good thing about these compression methods on your right here is that since they are particular for hydrogen, and they make this compression technology even more versatile. If we compress it, we can store it different places, and obviously this depends on your use. In the case of underground storage, we imagine that we need a lot of hydrogen. We don't use this for a small quantities, but for large quantities. And you see here that it's fairly high pressure. Now, what is the problem with this underground storage? It's the problem that you might get some impurities in your hydrogen, which can be problematic for your end use. So there is some research effort going into investigating if you put hydrogen into this reservoir. It can be an old reservoir used for oil and gas, or it can be a salt cavern or whatever. Will the hydrogen that you store there be destroyed by bacteria or other bad stuff inside your reservoir? For more practical uses, you can use tanks. And then you see here that you have tanks that are suited for different pressures. And obviously, we don't care about the structure of these tanks, but we just see that we can go from 200 to 700 bars, which is the typical storage pressure. Now, what we should be concerned about is the weight of your tank. So you might imagine that if you store hydrogen, it's not the hydrogen that is the biggest weight, it's actually the tank weight. So if we look at this typical all metal tanks, they will have a very high weight of tank per kilogram hydrogen. But if we use modern material, composite materials, we can go down and have a light tank as possible. So for instance, for high pressures metal tanks, you can get up to 80 kilograms of tank per kilogram hydrogen. But for more lighter composites, you can go down to maybe 19 or 18 kilograms per kilogram of hydrogen. This matters because when you transport hydrogen, you need to be mindful of the weight of your entire system. Another possibility is to liquefy hydrogen. And in the world today, we have two main ways of doing it. Is what we call the helium-Brighton cycle or the Claude cycle. And these cycles, they are industrial processes that exist in the world today. And for instance, in Norway, at this point, we have no liquefaction possibility. And Dylan showed the picture of the Nordled ferry, and it uses liquid hydrogen. So the question is, where does it come from? It comes from a truck from Germany. What is important with liquefaction is that we really need to have a fairly large scale for it to be cheap enough. So as you can see here, typically we divide these facilities into small or large scale, and we set separation limit by about 3 tons per day. So the thing is that actually it's very difficult to get down to this minus 353 degrees Celsius. No matter how we do it, we can use liquid nitrogen for pre-cooling, but then we need to cool the gas even more. So we can use helium or hydrogen to cool the gas even more, but in the end, to get down to minus 350 degrees Celsius, we need to really use some advanced method to be able to do so. It's not enough to cool hydrogen with other gases. So this is a highly specialized process which requires a big infrastructure. You can see here on the process schemes that it's not an easy thing to do. And you can see here also that it requires a lot of pumps and valves and purification of the gas. Okay, so what's the most important things to know about the small scale versus the large scale production? So obviously for small scale, we have a relatively low capex, like investment costs, but we have a high operating cost. And for the high scale, it's different. The plant is more difficult to build and more expensive, but it has a lower operation cost. So obviously, and it's a general rule I think you all know about, the larger the production volume, the cheaper it is in the long term. However, these two process facilities, they are not how to say it, easily built. And what you will see later is that we need to be really careful about how we set up our production. Because what is the point of liquefying hydrogen if you have no end customer? And you can also imagine that if you produce a lot of liquid hydrogen, your end customer needs to be within a certain distance, because this liquid hydrogen is at minus 253 degrees Celsius, so it doesn't stay liquid forever. And so you can store it in specialized liquid hydrogen tanks, but they are not cooled. That means that after some time, the liquid hydrogen will go over in the gas form. So you might say, in a sense, that you are on the clock after you have liquefied hydrogen. Then the obvious question is, why do we liquefy hydrogen? It's as a complicated infrastructure of this plant. It's really kind of difficult compared to just compressing it. With compression, you can use regular methods, but you see the answer here. So in these two cases, we have the same, about 4.4 tons of hydrogen, but the problem is that the footprint, the area of your tanks, it's about 4 times as much as when you compress it compared to as you liquefy it. And again, remember that hydrogen is one thing, but the mass of the tank surrounding your hydrogen is another issue. And you can just imagine that this is the same amount of hydrogen, about 4.4 or 4.7 tons, but this is the compressed form, and this is the liquid form. So if you were to transport this, your transport cost would be much greater. If you care about the size and the weight, and that is all for your transport, but not only for transport, it's also for your end use. So let's say now, for instance, that you want to use this on a boat. Maybe you will not have this volume available, so then you should use liquid. And for instance, this Norway ferry in Norway, it uses liquid hydrogen. And you can also imagine that it's a bit problematic to use liquid hydrogen because it needs to get it driven from Germany. But imagine on a boat, you will not have this volume available. You will probably be more easier off with this volume. So it's a complicated weighing of different ways of storing hydrogen and different ways of transporting it, and also where it's produced. Okay, what alternatives do we have? So we can also store it as a chemical. And the reason for converting it into something else, it's because we have a lot more experience with, for instance, ammonia or methanol than we do with hydrogen in terms of safety and use, especially in the transport sector. So in the case we need to use the pure hydrogen, we need to first make ammonia and then convert it back to hydrogen. So obviously this requires some energy that we lose. But as you can see here, ammonia, for instance, is liquid at minus 33 degrees Celsius. It's much easier to handle this than this minus 253, which you have for liquid hydrogen. Also, for instance, methanol, which is another option, is liquid at room temperature. And ammonia in particular has been used as a coolant for ages. So we have to have a lot of experience with it. As Julia said, hydrogen is not toxic, but ammonia is. So if you smell it, you have a lot of time until it gets dangerous. So you smell it about 5 parts per million. So if you have 1 million molecules, if 5 of them are ammonia, you can smell it. And then you start getting problems at about 200 to 400 parts per million. And then from about 3,000, you die at prolonged exposure. So ammonia can be quite dangerous. And if you use ammonia on a ship, where would you go if you have a leak? We have known technology for transporting and storing these chemicals, and we know that as we can store it at room temperature or an atmospheric pressure, or at least for ammonia, we can go to minus 33 degrees. It's not really a risk for us. Imagine that you have hydrogen at 700 bars. It's a big risk with the pressure. Finally, we see that in terms of energy density, ammonia at least is comparable to liquid hydrogen, which makes it a very nice medium for transporting hydrogen. Another option is this chemical storage in terms of this liquid organic hydrogen carrier. And what I want you to focus on is this picture here and here. So here you can see that you have 2 different variants, one loaded with hydrogen and one not loaded. And the thing is that what do I mean by this? I mean that this is an oil in both cases, and if I had it in front of me, you would see that it resembles an olive oil, or it almost has a water-like appearance. And the good thing with this is that we can just transport it in a regular manner. We don't need to use specialized equipment at all. Again, we have this advantage with room temperature and atmospheric pressure, but you see that if you have a kilogram of this loaded substance of hydrogen, which we have here, you see that it only contains about 7% hydrogen. So a lot of these are other substances, carbon, for instance. Why do we want to use this? It's good in terms of safety, but it's also good in the terms of the weight here. You can see that if we take hydrogen on or off, it doesn't really matter. The weight is almost the same. So if you use it on a ship, for instance, you need a stable weight. And then you can use this to compensate for your ship's weight, and you don't lose it as you will do if you use hydrogen. So if you use hydrogen on a ship, for instance, it will go away. So this remains as a hydrogen carrier on your boat. Okay, you have all these methods of storing hydrogen, and then obviously you want to transport it. And the question is, how do we choose our correct way of transporting hydrogen? You can think of it in two ways. We have the hydrogen quantity on the x-axis here, and we have the distance from the end-use source here. If you have a very small quantity, maybe it's nice to use compressed hydrogen. You remember this large amount of tanks, right? But if your quantity is very small, this is okay. At some point, you need to consider, maybe I should liquefy it, either if your quantity is really big or the distance you have to transport it is really big. In the end, okay, you have so much need, or your distance between your production and site is so big, and your use site is so big, that you need to consider to have on-site production. So I will show you soon that on-site production may be useful in some cases. Another option, as you can see here, is using the pipeline. The problem with pipeline is that, for instance, a country like Norway, we have very little pipeline that is suited for hydrogen, maybe nothing at all. So if we are to construct the pipeline in Norway, it will be extremely expensive, because Norway, it's a terrible country in terms of mountain and ridges and so forth. And also the fact that we are really sparsely populated. But it's a good and valuable possibility if either you have large consumers, or you have existing pipelines, which is true for some countries in Europe and perhaps also India. Okay, as you see here, it has some kind of magical distance where you should at least consider using liquefied hydrogen instead of compressed when you transport it. And before, this was about 250 kilometers. So this is one way of saying it. But then, as you can see here, you just really consider these two options, compressed or liquid hydrogen. But you can also see that the reason we care about it is it has a lot to do with the cost. So you should remember that when you use hydrogen, you pay not only for the production, but you pay for the production of hydrogen, the storage, and the distribution. We can continue to look at this even further. So this is more about the price and how it turns out. Again, we can think about the distance you have to transport it, and we can have now not the quantity, but the cost per kilogram of hydrogen. And the way this works is that you have different alternatives. You have the pipeline, you have liquefied hydrogen, you have the liquid organic hydrogen carrier, which is the oil type, you have ammonia, or you have compressed hydrogen on the ship. And in this research, they have kind of compared all these different possibilities. Now, if this line, you see that all the lines are stapled, but if it's solid, that means that it's the cheapest alternatives. So for distances, and now we are at large distances. This is about this is 5,000 kilometers, so it's a long distances. So in the beginning, it's nice to use this hydrogen pipeline, but the problem is with pipelines in general, the pressure, it's only about 100 bars, which means that the hydrogen density inside the pipeline is not that big, so large. So at some point, you have to change from pipeline to liquefied hydrogen. Liquefaction has an issue right now that if you use the tanks that we have for storing liquefied hydrogen, they have a lifetime about 14 days before the temperature starts to get so rise as much as it will start to convert into gaseous hydrogen. So you have some time constraint here in a sense. But for long distances, for distances between about 3,000 and 17,000 kilometers, liquefied hydrogen is a viable option. At some point, almost every method becomes problematic. If you come to really large distances, you should consider this oil type of substance because it has kind of like an unlimited lifetime. If you have it in a tank, it will stay there for forever. So with liquid hydrogen, you have the problem that it will turn into a gas eventually, and with the pipeline, you have the low density. Furthermore, you should be just mindful of the volumes here, because if we have a comparison between hydrogen and ammonia, you can see that in terms of volume, ammonia has an advantage. But also, again, if you continue, you see that liquid natural gas, it's even better. But the problem is now, and that is the kind of basic line, we want to move away from fossil sources, and then it's ammonia and hydrogen, which is are the most perhaps viable replacements of fossil fuels. Okay. For instance, in Norway, we have our country here, so it's more than 700 kilometers long. And we only have in this country, large country, about 5 million inhabitants. So how can we solve this? Pipeline, maybe not such a good idea, because Bergen, which is the second largest city, has 400,000 inhabitants, but Oslo, which is the largest, only has 1 million. And you have all these small cities here, and you have a lot of population in between. And for instance, let's say in Norway, you wanted to move or use compressed hydrogen, it's about $2 per 500 kilometers per kilogram. So this is actually an additional cost of about $2 if you transport it. And it's not really viable if you think of hydrogen as a competitive fuel in terms of price. Now, how can you solve this? One solution is obviously to use localized electrolyzer production. And as you saw, an electrolyzer is just something like this, but obviously much bigger. And you can put some power on it. And a good thing about Norway is that we have a lot of mountains, which means that we have a lot of falls, which give us electrical power. So in Norway, this trapped-in power, or for instance, as Velo said, wind power is a viable option. And then you can imagine that instead of having any type of hydrogen transport, you put localized hydrogen production where you need it and couple it to a variable energy source. Okay. Then we move on and talk a bit about the hydrogen use. So actually, this is a really, really complicated field with a lot of uses. So what we can imagine, and in this context, we talk a lot about hydrogen in terms of it being an energy carrier for the transport sector. So we want to use it in our cars and ship as a fuel. But we should always remember that hydrogen is also a chemical. It can be used as a chemical with the same purpose as a fuel to reduce CO2 emissions. Why is hydrogen such a good thing? We have seen it already, but it's nice with a little repetition. It's a very nice kind of a match with renewable energy, because renewable energy sources like wind and solar, they go like this, like up and down, and we can couple it to hydrogen production and storage and use hydrogen as an intermediary battery when we have, for instance, power shortage. We can put hydrogen back into a fuel cell and make power. Okay, let's just stop for some small time and reflect on the why we want to use hydrogen. So what we have seen up until now is that it can be produced if we want to from completely renewable energy like wind or solar coupled with an electrolyzer. In that context, it's CO2 free, and it can be a nice battery for wind and solar power harvesting. It's complementary to electricity in the sense that you can use electricity to produce hydrogen, and we'll see later that you can put hydrogen and oxygen into a fuel cell and make electricity again. It has a high weight-based energy density, which is good for us. But are there some issues? So, for instance, how do we secure the power to produce hydrogen, the electrical power, if we want to use a renewable method? And even though we will use a fossil method, how do we really make sure, because we don't have unlimited natural gas, right, which Julia showed was one of the ways of producing it. So how do we make sure we have either natural gas available, or if we want to leave that track forever, how do we make sure we have enough power? Because power should go into the grid if it's needed on the grid. We should only use it to produce hydrogen when we have a surplus of power. As you see, we have a low energy density per volume, which is problematic, for instance, on a boat. And we have energy loss during production. Compression to 700 bars, maybe 1,000, that requires energy by itself. And also liquefaction to do the purification of hydrogen and the cooling of hydrogen, and then finally making it into liquid, requires a lot of energy. And finally, how do we get a proper distribution? So we saw right now that it might be problematic to have it transported in a country such as Norway. We should be mindful of the pros and cons as we go into this field, because the end goal, I hope for everyone, is to try to make hydrogen technology as sustainable as possible. If we're going to use, we'll just briefly talk about how we can use it to generate electricity or in the means of transport. So one possibility is obviously to use an engine. And today you have hydrogen engines and you have ammonia engines. And the point is that they can be used as a conventional engine in a sense. If you design an ammonia or hydrogen engine, you need to design it differently, but the principle is the same. You put in your fuel and you get energy to drive your engine from the fuel. So a hydrogen engine, what we have done today is a lot of rebuilding of conventional engines. And the idea is that you can have a combustion reaction with hydrogen and oxygen. And obviously, in this type of engine, your exhaust is water. It has been shown that it works well, but the problem with this type of engine is that in a lot of cases, it will really generate a lot of heat, because the hydrogen combustion is really kind of intense and generates a lot of heat. And what's the problem with that? The problem is that you can get the formation of this NOx. And NOx, like nitric oxides, they are also greenhouse gases. So even though the reaction itself is harmless, hydrogen, oxygen burns and you get water, the temperature and the fact that you have nitrogen present, if you use air, for instance, then you can have the formation of new greenhouse gases. And you see the problem also that even though your starting point, H2, it's a green chemical, there's no carbon here, it's not petrol or gasoline, the efficiency is low. Or it's not low, but it's comparable to a regular combustion engine, which we now think it has too low efficiency, basically, in this new green transition. One other option is to use ammonia. Same thing here, actually. It has harmless products, but again, you have this possibility of NOx formation, which is harmful to the environment. And again, you have this problem with the efficiency. It's very low, actually. But today, for instance, Norwegian companies like Wärtsilä, they have designed engines that are about 50 to 60% efficient. So it's not completely dark, but we still imagine that these efficiencies are too low. In the case of ammonia, you also need to work a bit to get it on fire, so to say. So these engines, they are customly built for ammonia. And in both the case of hydrogen and ammonia, you need to be careful when you make your engines, because ammonia, highly corrosive, and hydrogen can lead to embrittlement. Another option is this fuel cell option. And what is good with this is that at least for the low temperature kind, at least.
I'm sorry, Prashant. Can you please mute yourself?
At least for the low temperature fuel cell, you have some very nice advantages. First of all, it's at low temperature, so you don't have this problem with development of greenhouse gases like you would from combustion. There is no nitric oxide formed here. And again, your exhaust is only water. And you see that now we are talking. The efficiency of a fuel cell, 65% and climbing. There is a lot of research going into increasing the efficiency of fuel cells. You can also here use ammonia. But here comes the problem. If you want to use ammonia, you need to use this high temperature type of fuel cell. If you want to use ammonia in a low temperature fuel cell, you need to convert it back to hydrogen first, which requires a lot of energy. So there is a problem, right? How to choose your end use based on your hydrogen carrier. If you have ammonia, perhaps you should use the high temperature SOFC fuel cell. And also kind of the remark I wanted to make is that regular combustion engines, they are below 50% in efficiency, but as you go from combustion engines to fuel cell, you get up to above 50 and maybe up to 65 or 70. And then I would also like to just address a quote from a very famous chemist and physicist, Oswald, in 1894. So he actually said that we have a galvanic element which gives electrical power. And we should use this invention to push back the invention of the steam engine. And he says, imagine the appearance of our industrial places. There will be no smoke, no more soot, or no more fire. So even in 1894, this fuel cell was kind of compared to the combustion engine. And then in that time, it was not a combustion engine with hydrogen or ammonia, it was a combustion engine on fossil fuels. And they wanted to go in the fuel cell direction, because as you can see here, it's just hydrogen and oxygen coming in and water going out. And then obviously the question is, why didn't they? And the reason they didn't was because the steam engine, much easier to fabricate and use than a complicated fuel cell. In general, electrolyzers and fuel cells, they are really, really complex structures. So in the 1800s, the engine won, and now we are kind of making the fuel cell reappear and take the place of the engine, or at least the engine that goes on fossil fuels. Okay, I think it's worthwhile just to reflect on the energy density. So what we actually want to look at is the fact that we can compare it to batteries. And the reason I want to make this comparison is because that in the use of hydrogen, we should also be mindful of the fact that batteries and fuel cells, they should coexist. So fuel cells, they should be together with batteries, because the battery will protect the fuel cell. And this is the point of this slide, to show that we have this cooperation. And why do I stress this? I stress this because a lot of people, they say that all these technologies that I present today, they are competing. But what we should take home from this is the fact that these technologies, they are not competing. Batteries, they have the possibility to help fuel cells in the energy system, and fuel cells will aid the batteries. So if we, for instance, look at different types of cars as a point of in our use, we could have electrical, or we can have hydrogen cars. So the thing with the electrical vehicles is that the efficiency, it's typically much better. And this is why we want to use battery cars. And at least in Norway, we would like to use, we use our hydropower, and we have a big electrical car industry, which is partly has been supported by the government. And the reason is, there's a lot of reasons, but one of the good reasons is because of this energy efficiency. Okay, we can also use a hydrogen car. Hydrogen cars in Norway is difficult because we don't have sufficient filling stations. But if we look to Europe, we have a lot of trucks around Europe. At this point, we have 27 in Germany and 47 in Switzerland, right, for in trucks. And the idea is that, again, having hydrogen-driven vehicles, it's easier in Europe compared to Norway. The question is, can we use hydrogen also for other types of transport? Obviously, we can use it for ships, like Dylan said. We can use liquid hydrogen in the passenger ferry, but we might also be able to use it in airplanes. So airplanes right now, they are going through the same transitions as trucks and cars have done, and also that the shipping industry is doing. They're trying to look into new fuels. Liquid hydrogen will most probably be the dominating aviation fuel in the future. The problem is, and this goes for all these types, typically it's you need to have some infrastructure. And the question is, how do you make this infrastructure? So for instance, in Norway, and typically it's easier to get electrical infrastructure than hydrogen infrastructure. And this is a question about security, but also distribution. Again, you should be mindful of the fact that this is a very country-specific problem. Again, in Norway, we have very, very few filling stations because we are a sparsely populated country, but this is different in other types of the world. Why do we want to have a combination of batteries and hydrogen in our systems? We want them because we want the fuel cell to live as long as possible. If we have a hybrid vehicle, we can use the fuel cell in a very friendly manner to the fuel cell. We can have it operating at constant load. And fuel cells are particularly interested in operating at constant loads. They do not really handle load variation that well. By using it together with batteries, we can have the battery do the peak shaving. They can do their work when we have the need for instance, acceleration. And they will protect the fuel cell, because if the fuel cell needs to go up and down, it will be destroyed faster. If we in a system want to use fuel cell and batteries, we have the problem with the fact that it depends on your driving pattern, and it depends on how much you use your vehicle. So for instance, if you have a truck, your system will look different than if you have a car that will drive in small streets. And to optimize this battery hydrogen system, it's an ongoing research, which has it's been working a lot with. And also the same applies for the maritime industry. So if you want to put a fuel cell on a boat, for instance, you can use advanced models to predict the load in the future. And as Velo said, in this high-value research center, we look into how to, for instance, predict the load that the boat will experience in the future. Because if we know how much load we need in the future, we can optimize how we run the battery and fuel cell system. Okay, finally, I want to bring your attention to the fact that hydrogen, not only a fuel, also a chemical. And this is a titanium oxide power plant in Norway. It's located inside the fjord, and they produce this titanium oxide, which is a pigment. And right now they use CO as a chemical to make this titanium oxide. But they have gotten money from the Norwegian government to try to replace it with hydrogen. So again, you get this pigment out, which is used, for instance, in white paint. But you see here that the chemical you use to start with is hydrogen. And if they're able to do it, they will cut their emissions from 5.1 megatons now to 0 in 2050. So you should be mindful of the fact that hydrogen, indeed, it's not only used for transport, it's also an important chemical. Okay, so now we can look again at our pros and cons. We can put the fact that it's not only used for transport, but hydrogen can also play a role as a green or emission-free chemical. Again, we can say that we have some energy loss during use. So we stopped last time with this proper distribution, but now when we talk about the use, we have an energy loss. And what do I mean by that? I mean that engine has an efficiency of 43%, or a fuel cell has an efficiency of 65%. That means that you lose about 30% of your energy that is stored in your hydrogen when you use it at the end use. So these efficiencies, they matter, and we will lose some energy when we use hydrogen. Also, even though I want this to be different, hydrogen fuel cell or ammonia engine or hydrogen engine is at this point more complicated than conventional engines. So this is an inherent problem that we are trying to solve with hydrogen technology. Okay, we are nearing the end, and I hope that I can tempt you with studying this further. We are planning, as Dilan said, a hydrogen course for managers and administrators. And now you have gotten a taste of everything in a very short period of time. But let's imagine now that you did this again, but you used 6 times as long time. Then you would be able to better understand the things that we have been talking about today. In this course, we'll talk about hydrogen's role in the green transition, and also all these types of hydrogen: compressed, ammonia, liquid, how we use it, when we use it, how we produce it. And obviously also, we will go into more applications of hydrogen technology. And a topic that we have touched today, but not nearly enough: how do we use hydrogen and its carriers in a proper manner, in a safe manner for you? So, for instance, if you have it on a boat or in a car, it's not dangerous to you. If you take this course, we will also discuss if there are hydrogen regulations and laws in India. I hope that it will be partly physical, that I can come to India or Sri Lanka and start the course, and then that the rest can be digital. And you should be able to choose either getting credits or to get a diploma. So then I just want to conclude and say that I hope that you found this presentation useful and that you have learned a bit more. And you can maybe think about in the future, how can we make hydrogen technology sustainable in the green transition? Then I would like to thank everyone for your attention, and I think I give the word to the organizers.
Sibyl? Devi?
Yeah, yes, sir. So is there any more session from your end, Jonathan?
Yeah, I think we will have a techno-economical session after the break. I think if we have time, we will have a new break now.
Yeah, we will have a break now.
Devi, you can make me
We'll
free.
have a break now, 15 minutes, and then we will join for the question and answer session. And we have a session with Uda Maria as well, isn't it?
Mm.
So we'll meet in 15 minutes.
Fair enough.
Devi, can I leave?
Yes, sir.
Okay.
So we will meet in 15 minutes from now.
Yeah.
Thank you.
Sure, sir. Sure, sir.